Welcome to this video on Marcus theory in organic semiconductors. We will explore how quantum mechanics principles lead to material design insights, focusing on non-adiabatic charge transfer and computational screening. Charge transfer in organic semiconductors is better described by Marcus theory as a localized quantum hop between molecules, unlike the delocalized motion of band theory. This hopping mechanism is key due to the weak intermolecular coupling. The quantum mechanical starting point uses the diabatic basis, where the charge is localized on either molecule I or J. The Hamiltonian includes potential energy surfaces, the nuclear kinetic operator, and electronic coupling. The reaction coordinate Q is a complex, many-body collective coordinate. Free energy surfaces are often visualized as parabolas, assuming a harmonic nuclear response. Key parameters include the activation barrier, delta G, the driving force, delta G0, and the reorganization energy, lambda, which is the energy needed to distort the nuclei. The semiclassical rate, Kij, originates from Fermi's golden rule. It consists of an electronic part, representing molecular torque, and a nuclear vibronic part, which accounts for nuclear arrangement. This leads to the Marcus rate equation, which combines quantum transition and classical nuclear statistics. The Marcus equation is governed by three factors: the electronic coupling, Vij, the driving force, delta G0ij, and the reorganization energy, lambda. Strong coupling and minimal contortion lead to faster charge transfer. Holes and electrons require different surfaces for transfer. Hole transfer involves HOMO-like states and cation geometry change, while electron transfer involves LUMO-like states and anion geometry change. Different couplings result from these distinct processes. The computational workflow involves 6 steps, moving from static quantum chemistry to dynamic, macroscopic stochastic transport. The first 3 steps are getting solid-state geometry right, computing reorganization energies, and determining pairwise electronic couplings. Steps 1 and 2 focus on morphology and reorganization. A credible solid-state geometry is essential, as couplings depend heavily on orientation. The adiabatic 4-point scheme is used to compute the reorganization energy, lambda, by optimizing neutral, cation, and anion geometries. Steps 3 and 4 involve pairwise couplings and driving forces. Extracting dimers from the morphology is needed to compute electronic coupling, Vij. Realistic films require calculating a pair-specific driving force, delta G, due to site energy variations. Steps 5 and 6 solve the macroscopic transport problem. This involves building a hopping network and incorporating thermal disorder, using techniques like molecular dynamics and kinetic Monte Carlo to compute mobility, mu. Marcus theory highlights that charge transfer is controlled by both electronic coupling and vibronic overlap. The tractable targets for design are reducing the reorganization energy, lambda, and improving intermolecular coupling, Vij. Marcus theory is a specific asymptotic limit, assuming localized states, weak electronic coupling, high-temperature classical nuclear motion, and harmonic free energy surfaces. It is excellent for disordered materials, but may be misleading for highly ordered organic crystals. Practical design logic focuses on minimizing lambda by favoring rigid backbones, maximizing Vij for multiple strong transport pathways, and minimizing energetic disorder. The golden rule is to optimize these targets while remaining in the localized hopping regime. In synthesis, a charge hop is a golden rule transition between localized electronic states enabled by nuclear fluctuations. In the weak coupling limit, this becomes the Gaussian Marcus rate, defined by electronic coupling, reorganization energy, and driving force.